Hey everybody, welcome to the video week 20B. Just want to say thanks for the really great comments that we had this week. If you are not in the habit of reviewing other people's comments, then I really want you to do that. It only takes a second to skim through and see what other people have written. A lot of you write the exact same things, so you can see what I said to others. And it's really good to leave comments too. I'm going to call out Nolan. Nolan is very good at doing this. Writing in answers to other people. Teleos has done a lot of that too, so keep it up. It's really worth it for you to try to weigh in on other people. Now, for this second video, I'm actually changing up our curriculum a little bit from what I had planned months ago. You guys have had so many good questions about Hooke's law, and I'm just deciding, you know what? I think I want to continue to talk about that a little bit more instead of what I was going to do, which I think would be, just more of a departure and more confusing potentially. So we're going to hang out on this. Hooke's law, and then also lots of questions on Young's modulus, lots of questions on things that break, when do things break, how do they stretch, there's a lot of really good ideas about this, and I want to try to wrap that all together in this lesson, and then we'll see kind of where it goes from here as well. Maybe we'll camp out on this some more. So in this video, there's 4 terms that we are going to describe, and those terms are as follows. We have stress, we have strength, we have something called strain, and then we have elasticity. All right, now all of these words, let's see, all of them can be measured with like actual units and numbers. That they're not just sort of vague ideas. They are measurable quantities. And before I go any further, I just want to say too, please take notes on this. Please get a calculator as well. If you don't have a calculator right nearby handy, you want that. I want you to actually type in some numbers yourself. There's going to be a lot of numbers coming at you, and I don't want you just to watch me doing it. I want you to try to beat me to the punch. That makes you a better student, a better engineer, better mathematician, all of it. And again, also, before I get into what is stress, what is strength, what is strain, what is elasticity, they're all words you kind of use in everyday language, but we have particular definitions for them. I just want to remind you of your prefixes. Okay? You have particular prefixes in the SI units system, and the ones that are going to make their appearances today are these 3. Okay, kilo and mega and giga. Kilo is when you times something by 1,000. Has to be a small k. Mega is when you times something by 1,000,000, like $1 million. And giga is when you times something by 1 billion. Okay, 9 zeros. So this is a definite like order, very sequential. Kilo, mega, and giga. So you'll see those. I want you to know what they mean. We have mentioned them in the first semester. Okay, so back to the idea of stress, strength, strain, and elasticity. Now, all of these things, they're all to do with how a particular material behaves. Okay, everything that you touch around you is made up of different materials, whether it's wood, steel, aluminium, carbon fiber, cardboard. And I'm kind of talking about like solid building materials here. My wedding ring is made of palladium. You might have a titanium piece on an aircraft carrier. You might have ceramic components in an engine. And you really want to know, how do these materials behave? So there is a particular branch of science and engineering called materials science, and this is a specialization that, like if you wanted to, you could devote your whole life to materials science. how does stuff behave? The stuff that we want to build things out of, how does it behave? How do you understand it? How do you measure it? How do you invent new types of stuff that does exactly what you want? It's kind of an interesting field, and that may be something you choose to go into one day. Now, I know I keep on giving all these little preambles, but here's one more little preamble before we get into it. Everything that we are dealing with here, stress, strength, strain, elasticity, these are all what is known as intensive properties. Okay? Intensive properties. That's all of these. Okay, it's in the blue to match up. This is as opposed to other kinds of properties, which are called extensive properties. Now, I don't know if you have used these same terms in chemistry with Mr. Hooke for 11th and 12th graders, but an intensive property, that is where the property of the material doesn't change whether you have more or less of it. So something like, for example, density. Okay, there's my example. Example, density. I don't know why I have those parentheses there. Don't need that at all. I'm just going to erase that completely. Like if you have a small piece of wood or a large piece of wood, it doesn't matter. If it's the same type of wood, it has the same density. Okay, wood is going to be a particular density. Now, this is different than extensive properties. An example of an extensive property, maybe you can guess what I'm about to say, would be mass. A small block of wood has less mass than a big block of wood. Mass scales up or down with what the size of the object is, whereas density doesn't change. So density is the intensive property idea. Mass is the extensive property idea. Another extensive property might be length or weight. Another intensive property might be, I've got to be careful here which ones I pick. Let's stick with density. Density is a good one. And then I've got 4 others up there: stress, strength, strain, and elasticity. Okay. I want you to picture a piece of steel. We are going to just talk about steel for this whole lesson. I'm just going to really tighten the focus, try to keep it as simple as possible. This is a rectangular prism. Nope, let's use a darker color than that. Let's just use the black. This is a rectangular prism. Okay, actually I'm looking to make a square end. There it is, my little piece of steel, and I do mean little. I want to say that this piece of steel has dimensions of, you know what? I'm sorry. I apologize. I just really feel like I should do this one a little bit bigger. I think I went... There you go. Look at all these 3D markings. Okay. Now, it's a square end, like it's a square shape. I guess you could call it a square prism, or it is still a rectangular prism if you go at it from the other way, if you know what I mean. And let's say that our little piece of steel, it's not very big. Let's say it has these particular measurements. So 0.1 meters, in other words, that is 10 centimeters. Okay. In other words, that is approximately 4 inches. And then on this other end, that would be 1 centimeter, or if you like, that would be 10 millimeters. Okay, it's trying to give you lots of synonyms for the same exact thing. But I am going to try to just sort of talk in SI units to make it as simple as possible. But I was trying to give you a sense of the scale of this thing. It's a little 4-inch piece of steel, solid steel, not a tube. And we're going to use this piece of steel to sort of mentally, virtually test the intensive properties of steel. So let's do a few little calculations here, some things that I think you know. Let's do an extensive calculation. What is the volume of this piece of steel? So you may want to pause the video, pick up your calculator, even while I'm talking right now, punch out those numbers. How do you find the volume of a rectangular prism, of a box? It's an elongated box. Well, it is length times width times height. In other words, all three dimensions, all calculated, and that is going to be 0.00001 meters cubed. I'm hoping I got that right. Pretty sure I did. But there it is. That's the volume. That is an extensive property because volume would change if it were a bigger object. Let's calculate something else. I would actually like to know, it's going to become quite important, what is the cross-sectional area of the piece? Like if you were just to go and slice through it, what would be the area of that slice that you were looking at end on? Okay, this is called the, once again, the cross-section. Section from the Latin word to cut. Okay, like the secateurs used to cut roses with, or the dissection that you do in biology class. Those are all coming from the same Latin root. Let's see, the cross-sectional area, we'll just use A for this, capital A. It's those two numbers on the end. It's the 0.01 meters times the 0.01 meters. It's a square. So I hope you can see pretty readily that we have an area of 0.0001 meters squared. Again, I hope you had your calculator doing what I'm telling you to do, and you tapped those out and got to it before me. And it's in red. It's an extensive property. I will really try to remember to do extensive in red, intensive in blue. Now, you might notice too, by the way, that the SI units we're using, talking in meters, don't really lend themselves well to these smaller objects. We are going to stick with it. We'll keep everything's in meters and newtons. We'll use those prefixes that I mentioned. We'll use the kilo, mega, giga when we get to it. But yeah, it is true that using inches is actually really handy for sort of everyday sized little objects. Meters are really good for measuring like massive things like bridges and buildings. But you know, here we are with a little tiny piece. That's why we've got a lot of decimals. All right, the density. The density of steel, you might remember from first semester. This is the Greek lowercase letter rho. It is the letter R. Density of steel is, we know this from looking it up in books, it's about 7,900 kilograms per meters cubed. Okay, that's good. That is an intensive property. Okay, it doesn't change with a bigger piece of steel. And using the density is something, again, you just look it up in a table of values. That's what I do. I go to the internet and I say, what is the density of steel? Actually, I know that one from memory. We can take it from there and we can then do a mass calculation, because mass is, I don't know how far I'm going to carry this forward, but let's see. Mass is density times volume. Okay, mass is always given as density times volume. And so we have, I'm just working this out right now, 7,900 times the volume, get those decimals correct, 0.079. And that is measured in kilograms. Now, you may wish to instead say that is 79 grams. That would be great. That's a little more usable. A gram is about one paperclip. It's about 79 paperclips, this little solid block of steel. So, you know, enough to heft in your fist, but it's not going to I don't know, it's not going to be very useful as a paperweight if a giant hurricane comes through. Now, as I said, we're going to use this little piece of steel to test with. We are going to test to see how it behaves under load. Things like volume, area, density, mass, those are all kind of like pretty like boring properties. They're just what steel is, but it's not responding to anything that's happening. So let's get into some more of the kind of thing that we want to do. Let's say that on our piece of steel, we are now going to pull with a tension force. Okay. I'm going to pull with a tensile force or a tension force, and we're going to do 1,000 newtons. Now, Newton's third law, equal and opposite reaction. This is static, so everything has to be balanced. So it's 1,000 newtons on both ends. Just like in any tug of war, both ends of the rope feel the exact same force. So we are applying 1,000 newtons of tensile load to this little block of steel, just to see what happens. Now, how big is 1,000 newtons? 1,000 newtons is probably about as much as you can reasonably generate as a human being, without any like levers or jumping and slamming yourself into things. You know, if you're just going to like grab something and just pull it and stretch it with your own two fists, 1,000 newtons is about what you can do as a human. I'm using tension here, not compression. I'm just going to talk tension for this lesson because compression gets into some other weird things too, like buckling, which I've mentioned to some of you. But yeah, we'll keep it real simple. It's tension. It's acting like a rope. So this tensile force of 1,000 newtons, this creates stress. Okay? And we mentioned stress already. That was one of the 4 things that we're looking at in this lesson. So stress. Now stress, let's get into this. We need another Greek letter. This is the Greek letter sigma. We have used sigma already. We have used capital sigma, which looks kind of like a giant letter E. We use it for summing things up. Okay, just off to the side here, you remember that? That's our capital sigma. This is the lowercase sigma. It looks like a little letter O with a little kind of a tail, and that is like the universal symbol for stress. It starts with an S, sigma, stress, but it's the lowercase version. And stress is defined as force over area. Okay, stress is defined as force over area. So when you take a force and you apply it over a particular area, you get a stress, and it's a number, it's a calculation. And some of you may recognize this as the formula for pressure as well. Pressure is also defined as force over area. Pressure and stress are actually really kind of the same thing. Stress is a more versatile idea. Pressure is just like something pressing on something, usually a gas, but it is actually the same idea, 100% the same. So what kind of stress do we have here? Well, again, I'm trying to use red and blue very carefully. We had a force of 1,000 newtons, or you could say 1 kilonewton. And we have an area, we already said it. We have an area of 0.0001 meters squared. Okay, that was just a couple of lines back. You can see it on the screen still. So if you take the 1,000 and you divide it by the 0.0001, you're already on your calculator, right? You get a stress of 10 million watt. What are the units here? Well, let's think about these units. Force is measured in what? Newtons. Area is measured in, it's right here, meters squared. So that means that stress is measured in newtons per square meter. You know, it's a force applied over an area. Newtons over a square meter. That is such a common thing. We run into it so often that we actually use a special symbol for that. I'm sorry, a special unit. Sorry, units and symbols are not the same thing. And the unit that we use is actually pascals, named after the French mathematician, engineer, scientist, theologian Blaise Pascal. Capital P, little a. It means a Newton per square meter. Okay, it is used also for pressure, for stress. You'll see it in atmospheric pressure calculations. You'll see it in all the stuff we're going to do. 1 Newton per square meter is 1 Pascal. And let me just do this a little more as I would do it if I were doing this myself and not teaching. I would record that result as 10 megapascals. Okay, 10 megapascals. Because 10 million for mega, and I wouldn't say newtons per square meter. I would always say pascals in this case. Okay, 10 megapascals. I realize I'm saying pascals and pascals a little differently every single time I say it. I think I've just had so many different teachers and from different countries over the years, and travel to different countries, that I just kind of say things how I want, and I will be fine with you saying it how you want. Pascal was a Frenchman. I'm Australian, now American. Who knows? Okay, 10 megapascals. Now, is that a lot? Is that a little? Well, 10 megapascals, when it comes to something like steel, it's not actually that much. But when I apply the 10 megapascals to the piece of steel, as in this picture, that is what I'm doing here, the 1,000 newtons with that particular size of cross-section produces 10 megapascals. That makes the steel actually stretch, okay? It actually does get a teeny bit longer as I apply that stress. Now, for a little piece of steel this big with a little load of 1,000 newtons, 10 megapascals, it's not going to be perceptible, but we'll get a little bit more into that. But it does get longer, If I were to increase the load, I could keep jacking up the load higher and higher and higher. Eventually, what's going to happen? Well, this thing is going to break. Okay, my little piece of steel, my little baby steel piece, it will snap. And that brings me to the second term that I promised you, and that is the strength. So strength is it's the stress at which, a particular thing happens. There's several different strengths. The one we're interested in today is actually the ultimate tensile strength. And because people don't like to say that and type that a whole lot, we call that the UTS, the ultimate tensile strength. The ultimate tensile strength is the stress at which a piece of steel breaks. Okay, we also use the same term for aluminium, for beryllium, for titanium, for carbon fiber, for pieces of wood sometimes. It's just the strength at which it breaks. Okay, you pull on it, and then you suddenly see it go crack, it snaps. That stress that made that snap happen, that is the ultimate tensile strength. Now, what is the ultimate tensile strength of steel? Whoops. Well, it really depends on what kind of steel. There are all different types of steel. There's stainless steel, maraging steel, there's tool steel, there's carbon steel. There's all sorts of copyrighted, patented steels. And let's say let's pick real easy numbers. 1,000 megapascals is a very reasonable, typical strength for a piece of steel. It can be a lot less than that. It can be a lot more than that. It can be as much as double or half. But 1,000 is, right in that middle sweet spot, and it's just a super easy number. So we'll run with it. So that means that you can apply 1,000 megapascals of stress, and then you have reached the ultimate tensile strength and it breaks. Okay. Now we said that for our load that we are applying, we are only applying 10 megapascals of stress. So we are only like 1% of the way to the ultimate tensile strength. So we are fine. This piece of steel, we are not going to see it break by pulling with 1,000 newtons. I mean, wouldn't that be amazing if you could pick up a little block of steel, a centimeter by 10 centimeters, and you could pull on it with your fists and just snap it? No. In fact, you wouldn't be able to do that to a piece of wood unless it was maybe balsa wood. Even then, I think you'd have a hard time. Because materials tend to have pretty high ultimate tensile strengths. Steel does. Now, here's the question. What tensile force, now notice I'm using the word force, in fact, oh man, here I go. Let's be really precise. A force is definitely, come on. A force is definitely one of these extensive properties. So what tensile force would I have to apply to break this thing, to reach the ultimate tensile strength? Well, I pull out my lovely little formula, which I've just taught you. Stress equals force over area. And I say to myself, what is the ultimate tensile strength of steel? And I would say, well, it is 1,000 megapascals. Look at all those zeros. And then I'd say, okay, force, I don't know, but area, I do have. The area is 0.0001. And then I would solve for that force. And let's see, we got 1, 2, 3, 4. So we got 1, 2, 3, 4. I'm counting those decimals. If I have that right, that is 100,000 newtons. Okay, so what we're saying is, if we applied 100,000 newtons, or if you prefer, as I do, 100 kilonewtons, then this piece of steel is going to break. It's going to snap because we would have reached the 1,000 megapascals. All right, I know I'm throwing a lot of numbers at you here. I'm just going for it. There's a lot of zeros and decimals and all sorts of things. But we're doing well. We're actually about halfway through. And keep your eye on that formula. Okay, write down or put a circle around it, this one here. Okay, stress equals force over area. That's one of the big ideas. Also note, just to recap, so far we have defined stress and strength. Okay, stress is defined as the force over area. Strength is defined, at least the one we're using, the UTS, the ultimate tensile strength, is defined as when the thing breaks. And for steel, that's about 1,000 megapascals. All right, next little segment here. This is where if I were a radio show, I would have gone to an ad break, but I'm here. Before this piece of steel breaks, it stretches. I said that. Okay, I even drew it on a little picture. This piece of steel is going to stretch as we pull on it. Even if it doesn't break, it will stretch. Things always change size in response to the load. And how do you measure this? So the way we measure this is with our next word, strain. Okay, one of our magic words for today. Strain is an extensive property I'm so sorry, blue, intensive property. It's an intensive property. You might see why in a second. And strain is defined with this. Let me do that again. This lovely little Greek formula. All right, what is this here? Okay, we have lowercase epsilon, which is one of the Greek letters for E. Okay, E as in elephant, egg, Ermintrude. Epsilon is the symbol for strain. It's a little squiggly lowercase e. And strain is defined as delta L, that is capital delta, delta L over L. Delta, remember, we've looked at this already, it means change in length. Delta L, change in length. Delta always means a measurable change. It's the measurable change in length divided by the original length. Okay, strain is defined as the change in length compared to the original length. When you get into it, it's actually kind of an intuitive sort of idea. We're just saying it's almost like a percentage. It's like saying how much did this thing stretch compared to its original. Express that as a ratio. So here's what we've been dealing with. Now, forgive me for these numbers. I've tried to use actual true numbers. That's why it might get a little bit funny at this point. For our little piece of steel, when we apply 1,000 newtons, let's see, we applied 1,000 newtons, which then created our 10 megapascals. There it is. Notice how it went from being an extensive property to an intensive property. I don't want to get those wrong. I'm going to put a little note to myself. Extensive, intensive. Okay. We applied 1,000 newtons. That created 10 megapascals of stress. And let's say that we look at our little piece of steel, which was 0.1 meters long. Okay, we said that, 10 centimeters, 4 inches. And let's say that when we apply that load, we get our little teeny tiny ruler, or maybe some calipers, might be a better idea. And this thing gets 1, 2, 3, 4, 5. Let's say this piece of steel gets that many meters longer. Okay, again, why did I choose such a random number? Because this is what it would really do. This is a real value, okay? I've already gone ahead of you and worked it out, of course. So, okay, this little short stick, you apply that load, and you have these magical measuring devices which can measure this kind of thing very accurately, precisely, and it gets that many meters longer. So, just to make this totally clear, the total length is now 0.1000476 meters. Okay? It was that, now it's that, because of the applied load. So we run this through our strain formula. We say, how much strain is that? That's how much longer it got. How much strain? We had a change in length of 0.0000476 meters. We had an original length of 0.01 meters. What is that strain? And flipping over my page here. Let's see, if we divide by a little number, we get a bigger number. So we actually lose a decimal. 1, 2, 3, 4, 4, 7, 6. Dividing by 0.1 is like the same thing as multiplying by 10. So, oops. So that is our result, 0.0000476. And notice, this is really important, notice that for strain, there are no units. You can see in the formula, delta L over L, you're feeding in meters and then you're dividing it by meters. So as far as unit studies go, they actually cancel out and we have no units. It's a little bit like, as I said already, it's a little bit like a percentage. Okay, if you have 20 bananas and you eat 2 bananas, and I ask you what percentage, the answer is 2 bananas divided by 20 bananas equals 10%. But the word bananas drops out of it. You don't need to say 10% bananas. You just say 10% because that is, it's a ratio of 2 identical things, the original plus the part. That's what we're doing here. We're saying we're comparing the original to the increase. So no units. Now, why is all this important? Please tell me. Why is all this important? Well, it's because strain and stress and all these things, all these ones in blue, these are all intensive properties. And remember what that means. That means an intensive property is intrinsic to the material itself. It tells you about how all steel behaves. Even though we had a little test piece, 1 centimeter by 1 centimeter by 10 centimeters, we had that in our laboratory and we did the calculation, but that was a particular type of steel. If we now take that same type of steel and design a huge skyscraper or a bridge or a train or whatever it is, as long as it was the same type of steel, that intensive property is good for everything else that'll get made out of that steel. We know that all steel of that type will display a strain of 0.0000476 when subjected to 10 megapascals. Okay, that's the value in these calculations. It's actually incredibly important because we can't test the bridge. We can't build the whole bridge we want to build and then test it and see if it's going to hold up. What we can do is get a disposable piece of steel in the workshop, do that, and then apply the results to something much bigger and grander before we even do it. And practice over hundreds of years has shown that this method of laboratory testing and then extrapolating results actually really works really well. Okay, the last thing we said that we would do, going all the way back to the start, just to remind you, last thing we said was elasticity. What in the world is elasticity? Well, let me tell you. Elasticity is how stretchy a material is. This is actually Young's modulus. This is coming back to that idea that I've mentioned a few times. It's the Young's modulus of material. That's how we measure the elasticity. And here's the relationship. The relationship is stress equals capital E times strain. Okay. And what this is stress equals the Young's modulus, that's what the E is, the capital E, times the strain. That is the magic relationship which ties together the different things we're talking about today. Stress equals E epsilon, or stress equals Young's modulus times strain. So what are the numbers we've been talking about here? We had a stress of Oh, hold on. No, that's okay. That's okay. I'm using the right color. These are intensive properties. We had a stress of 10 megapascals. We don't know what a Young's modulus is yet. And we had a strain of 0.0000476. Again, no units. And so now you can actually work out what is the Young's modulus. What is capital E? And you get it by dividing the 10 million by the 0.0000476. And what you would get in this case is, if you do it to 3 significant figures, you will get 210 billion pascals. And I would way rather write that as 210 gigapascals. Okay, capital G pascals. 210 gigapascals. That is the value of the elasticity for steel. And actually this one is pretty consistently applied to many different types of steel. Steel varies from about 205 to 210 gigapascals in its stiffness and its elasticity. Now what I want you to see here as we sort of come to our last 10 minutes or so, this stress equals Young's modulus times strain. This is a proportional relationship. As in y equals mx, and not even with the plus b. This is a linear relationship. It's a proportional relationship because it doesn't have the plus b. It's just like, if there's double the strain, then it's double the stress, that kind of thing. If it's double the x, it's double the y. And it's very, very similar to the Hooke's law that I mentioned in the last video. In fact, both of these can properly be referred to as Hooke's law. And I hope that you can see the similarity. Okay, let's look at this for a second. In both of them, we have the applied load. There's the intensive version where we're talking about stress. Then there's the extensive version where we're talking about force. But really, whether it's stress or force, we're talking about what we're doing to the object. Okay, we're talking about the applied load. In both of them, you have the stretchiness. This one is the intensive version. This one is the extensive version. E, Young's modulus, that is talking about steel as a type of thing, okay, as a material. Whereas the K, the spring constant, that is referring to a certain object made out of steel, like this object right here in my hand. Not anything made out of steel, but this particular object made out of steel. If that object were a different size or shape, the K value would change. But the E, the Young's modulus, would not change because it would still be made out of steel. Okay? And then both of these two formulas have, kind of like what happens to the object. The intensive version has the strain, how much does this thing strain, okay, as a proportion of its actual size. The extensive version in the red has the measured distance x, which is how much, this particular object stretches by, whereas the blue version is like how much anything made of steel is going to stretch by as a proportion of its length. But they're both the same thing. They're both saying how much stuff stretches under an applied load based on the elasticity. They are both proportional relationships. They're both called Hooke's law. Okay, load is elasticity times deformation. Okay, a few little notes here. This law only holds for small deformations. I said this in the last video. It's very true and very important to understand that. This is such a simple relationship, but once you get into big deformations, big stretching, it just doesn't work anymore. I will show you. Actually, no. You know what? I'm going to skip that. I was going to show you something. Let's not do that. Let me show you how we actually use this in practice. Just one more example, taking what we just did and saying, hey, we're going to walk out of the laboratory. We tested our steel. We learned a few things about our test piece. Now, how do we apply that to some of the like truss stuff that we have been doing? Well, let's kind of make up a situation. Let's say you are a bridge designer. Let's make it more fun than that. You're a roller coaster designer. You design roller coasters. You have the dream job. You have the Mythbusters of all jobs. And on your giant roller coaster, you know, roller coasters are almost always, I think they're pretty much always made of trusses, big complex truss arrangements. And let's say you have this this one member of your truss, and you've done all the analysis. Maybe you ran it through a computer because there's a lot of members, but you have a, let's take a little imaginary slice. Here's the cross section. Okay, let's say the cross section is, let's keep it the same actually, 0.1 meters times 0.1 meters. Okay, 10 centimeters by 10 centimeters. That's actually still a pretty solid piece of steel. Sorry, I guess that was not the same size. Sorry about that. And this thing has a length of 5 meters. Okay, it's like a full-size truss piece. 5 meters is like 15 feet, 16 feet. And this thing has a load. This is a real-life thingamajig. It's out there in the real world. Let's say it's experiencing 1 meganewton, 1 million newtons. All right, with what we know, how can we analyze this truss? How can we say, is it going to break? Is it going to stretch too much? Because, you know, if there's too much deformation, that might be bad. If there's a roller coaster and your truss stretches too much, it might misalign the tracks. Something might, like the geometry of the whole thing might change in a way that we don't want. That's a real problem for large deformations. Let's work a few things out. We have stress is defined, as I said, as force over area. So what is that? We have 1 million newtons over an area like that. That is going to result in a stress, I'm just running the calculation quickly myself, of 100 megapascals, 100 million pascals. All right, that is the internal stress on this truss member. And that's quite a lot, 100 megapascals. So our first question that we probably want to ask ourselves, question number 1, has that reached the ultimate tensile strength, or even close to it? Is it even close to it? The ultimate tensile strength, we said earlier, is actually about 1,000 megapascals for a lot of different kinds of steel. So we are probably guessing that we're just fine. I'm checking that box. I think we're going to be okay. 100 megapascals is a lot, but it's only about 10% of a typical UTS for steel. So I don't think this will break. That's good. The roller coaster riders will live to ride another day. But second question. If the Young's modulus is 210 gigapascals, very common for steels, as I said, then how much will this piece stretch? All right, it's a big, long piece of steel. What's it going to do under that 100 megapascal stress? So you are going to say stress equals Young's modulus times strain. Okay, that is Hooke's law, the intensive version of Hooke's law. The load is the elasticity times the deformation. Okay, we just worked out what the stress was. 100 million pascals. We actually know what steel is. It is 210 gigapascals. And by the way, if any of you have been wondering why I'm not doing scientific notation, I'm just honestly trying to keep one more complexity out of all this, because I know there's a lot going on, and I'm relying on the fact this is a video that you can pause and rewind and understand, watch again if you need to. I wouldn't do this much in class live in the same 55 minutes. Okay, and then what we don't know is the strain, the epsilon. But we do all that. We divide 100 million by 210 billion, and we actually end up, if you run that calculation on your calculator now, it looks like, well, interesting. I guess it is the same number, a related number. You get a strain of 0.000476. Once again, remember there are no units because it is a ratio of two lengths. That is telling you how much, well, actually, let's use the formula. Strain is defined as change in length over original length. Oh, naughty me. Those are extensive properties. I think I've done pretty well. I think I might have got them all throughout this whole lecture. So we have a strain of 0.000476. And we had an original length of 5 meters. We said that. There's the 5 meters right there. So we multiply that number by 5 to see what we get. We get a change in length. You do that calculation of 0.0024 meters of stretch. Now this is the actual stretch. This is how much longer the piece of steel is going to get. 0.0024 meters. If you multiply that by 1,000, you get to 2.4 millimeters. Now 2.4 millimeters, that is actually perceptible. That's about like around 1/10 of an inch. It's, you know, the thickness of like, I don't know, 20 sheets of paper altogether. You can see that. This piece of steel, 5 meters long, which is, you know, probably half the length of the room that your classmates in, under the 1 million newtons of load, that is going to get about 2.5 millimeters longer. Just enough to see if you were looking carefully. I don't think 2.5 millimeters of stretch or 2.4 millimeters of stretch is going to be an issue. I'm going to check the box on that as well. We know what the stretch is, and we are probably going to be okay with that. Yeah, we'll trust that our roller coaster riders will ride again another day. All right, that was a ton of stuff. To bring it all back together, we looked at 4 intensive properties: stress, strength, strain, elasticity. Intensive properties don't change with the size of the object. They're part of what the object is by its very nature. We saw that stress is defined as sigma equals force over area, measured in pascals. Strength is the particular stress at which something breaks. That's what the UTS is, at least, and we'll keep it for that. We'll keep it at that. We looked at what strain is. Strain is defined as the change in length compared to the total length, the original length, I should say, and that is lowercase epsilon. And then we talked about elasticity. Elasticity is what links stress and strain. Stress is the elasticity times the strain, and that is simply the intensive version of Hooke's law, which we talked about in the last video. And then this walked you through how you might use those ideas in practice to get some of your like truss results or other things that we've done, and really see what they're going to do to change the object, to stretch it, to stress it, to strain it, to possibly break it. So that's a lot, but it's very useful what we just handled, and I think you guys can handle it. Please ask me if you have any questions. This does not appear on the assessment this week, but I think we'll pick up these ideas again next week because there is more that can be said. All right, thanks a lot. See you guys around.